All right. If you recall back a couple of videos ago, we talked about torque is basically an influence that might cause angular acceleration. So imagine that this is a door right here. And so what I want to do is figure out how do I actually cause this thing to close. I need to apply a torque. Right now it's in equilibrium. It's in rotational equilibrium as well as linear equilibrium. And I want this thing and I want to close it. Now, generally in class, I've got the door right there, and I use the door as the example. And then I ask, how do you close a door? So we're going to take something relatively simple, something that you've been doing all your lives, and analyze it. Now, because I don't have you calling out things, I'm going to give you some of the most common answers. And if you know the answers already, just sort of put up with this part. One of the common answers is, well, you push on the door. All right. So I want to close this. This is my door right here. I want to close it, and so I push on it. Well, that doesn't close it. Doesn't close it at all. And so there's more to it than just push on it. I want to close this as efficiently as possible also. So they say, well, push it in the direction you want it to go. All right, so which way do I want it to go? I want it to go that way or that way? Which way? That doesn't make any sense. And they say, well, push this way. So if I push that way, well, that only closed it so far. I could keep pushing. It will eventually close it that way, but it's not particularly efficient. Then somebody might go, well, push perpendicular to the door. Okay, well, I can push perpendicular to the door this way, and that's definitely not closing it. Or if I do it over here, I can push perpendicular to the door over here, and that's still not particularly efficient. And so ultimately you come to the fact that the push has to be perpendicular to the door, and you have to be as far away from the door as possible, and you have to push it so that in a sense in the direction that you want it to go. So you eventually get down to, and I milk this as long as I can, you have to push this way and push perpendicular, and that's the most efficient way. But this highlights several important things, and so I'm going to pause it here. So what we figured out is that torque, I keep doing that with torque. Torque depends on three things. The force applied, so magnitude of force, direction of force, applied, which just could be summed up as the applied force, and where force is applied. This gets summed up into a very simple equation. Simple looking equation is that torque is equal to R cross F. Now you might be thinking, wait a second, I thought we could just transliterate the old equation because isn't force equal to mass times acceleration? Well, yes, it is. So therefore, shouldn't torque equal I times alpha? Yes, it does. The difference between these two is this is the total torque, and this is the individual torque. Individual torque. So if I have a bunch of forces acting on an object, I would do this for each of those and then add them together to get the total torque, and then that would give me, and that's equal to I times alpha. Now, we've talked about dot products already, so this is the cross product. This is a little bit different. So I'm going to stop it here. We'll do a cross product video, and then we'll get into a specific example.